Officially, Chapter 3, it's the differentiation rules, the rules for taking derivatives of various kinds. What's that all about? So a big part of this chapter is looking at different types of functions and how to take their derivatives. What do we mean by that? I mean, don't we have the definition of the derivative, right? We're going to find shortcuts. We are going to shortcut the definition of the derivative that has the limit as h approaches 0. Um, so it turns out even in 2.8, when we had the definition of the derivative, even taking derivative functions, which was a huge step forward, we still have a little way to go before we really have something that is efficient enough for what we need to take derivatives. Even taking the derivative of something like the square root of x, takes several steps. We want to be able to do that much faster. So it turns out once we learn these derivative rules, we're going to be able to find derivatives in one step. There'll be these formulas. Most of them are formulas. Some of them are just an understanding of how it'll play out. Okay, we'll get to all that. Shortcuts to avoid limits. We're going to begin 3.1 with the simplest types of functions, polynomials. And it turns out exponentials we're going to throw in at the very end. Most of our discussion here is about polynomials. Turns out the differentiation rule for an exponential is very quick, so we can tack that on here in 3.1. Okay. So just to kind of summarize, I said this a moment ago, we're going to be using the definition of the derivative to arrive at these shortcuts. So we'll see the definition used in the lecture, but when we actually do problems, we'll know the formulas that were based on that definition and the shortcuts, if you will. But we are going to use that in the lecture. Okay. Also, just some more preliminaries. At this point, it's a good idea to introduce other derivative notation. So let me start off here. We've only been using one way to describe the derivative, and that's been f prime of x. Okay, we didn't want to overwhelm people too soon. So if you've got f of x, then its derivative is f prime x. And you could probably, easily imagine maybe we don't call a function f of x, maybe we say it's y, right? Y equals such and such. Then that derivative, we put the prime on the y prime. That's not too much of a stretch. But there are even more derivative notations. Okay, I'm just going to show you all these here. They kind of all get categorized the same way. I'll speak to that in a moment. So f prime x, if you want to keep the f of x notation, then another way to write the derivative is in front of f of x, put d over dx, and then f of x next to it. Now this notation is a bit funny, or it's a bit weird. This is not a fraction. This means the derivative of f of x, and you can very easily think of the little d as standing for the word derivative. Okay, what's up with the divided by dx? Why? There's a reason that notation is what it is and why it resembles a fraction. More on that later. In the same way, you could write d over dx with the y next to it. Okay, I mean, that's just kind of following the derivative of y. Okay. Also in the same way, and this one's helpful a lot of times, you can actually write what the function is inside there. So I put this little squiggle line. So d over dx and then some square brackets, and then actually write what it is. So maybe it's like x squared or square root or whatever. That one comes in handy. And then there's shorthand for these two. So instead of the f of x to the side, you could put simply f up in the numerator, df over dx. Or in here, instead of the y to the side, you could put it up in the numerator, dy over dx. Okay, now out of this list, you notice all of these with the d over the dx, they're called by this guy's name Leibniz. Leibniz notation. This is the notation that he used when he was developing calculus. So there's two guys. There's a long story about it. I won't go into. Pretty interesting. These two guys, Sir Isaac Newton in England and Gottfried Leibniz in Germany, developed calculus uh, really simultaneously, independent of one another. And it's a little bit more controversial than that. There was some correspondence between them, and Isaac Newton accused Leibniz of copying his work. Um, and but a lot of people stand behind Leibniz that no, he did not copy anything. Um, and it really caused a massive rift in the development of mathematics between England and the rest of Europe on the continent. Um, and just kind of part of that story, Leibniz was very, very concerned about notation. So he described a derivative with this d over dx sort of form, and that stuck. We still use it. So he was, you know, really wanted an easy to use way to represent this thing. And yeah, we still use his. The prime came much later. Turns out we don't use Sir Isaac Newton's notation for a derivative. They kind of see it in physics. Some it's got this dot. But yeah, that we really don't use that anymore. And the way the story goes, Leibniz, who when he was young, really vivacious, kind of very much a people kind of guy, throw big parties. He ended up because of all the tension with Sir Isaac Newton and just how influential he was. He ended up dying alone, and no one even attended his funeral. So, just kind of the story. I think like his secretary was the only one that attended his funeral. Where when Sir Isaac Newton passed away, he had a massive parade was held for him. I forget where it is in London, but there's this main road, and I'm just kind of blanking on it right at the moment. But I think most of us have probably heard of it. Okay, so anyway, these are the notations. The most popular between these are the f prime of x. We use that a ton. We use y prime a lot. That one's going to be a big one for us. Out of these four, actually the one that people go with is the dy over dx. You don't really see the f so much, or sometimes you see the y to the side, but much more likely to see this one. So we'll just go ahead and highlight that one. And then this one is just really handy because we can actually write what's in there. Oh, okay, I remember it. Sir Isaac, it's Westminster Abbey. So there's this. That's where he's buried. Huge tomb, all decorated. You can't miss it. Where Leibniz is like not even. It's barely even marked. I forget what town in Germany. Okay. So, what are we gonna do from here? So we'll kind of use some of these notations here and there in this section to kind of get a feel for them. All of these, if you were to speak the derivative, and this is like the formal words you would use for all, how many are these? All 7 of these, you would say it's the derivative of f of x, or maybe you would say the derivative of y with respect to x. You think, why is this respect to x? Like, why is that necessary? So it turns out we're going to see, the more usefulness of it in this course, and especially if you get to Calc 3, if you need to take Calc 3, you need to indicate which variable it's with respect to, because that's a multivariable calculus, and you need to be clear which one you're looking at. But even in this course, we'll see how that's useful when other variables start getting involved. Not technically multivariable, but we'll get it. Just to note, this is the dependent variable, the derivative of the dependent variable with respect to the independent variable. Okay, moving on. We would like to know derivative shortcuts for polynomials. So here's what we're going to do. We're going to try to get a formula for the derivative of f of x equals x to the n. So my question, what is the derivative of f of x equals x raised to any power n? And we're going to kind of hopefully discover this formula together. So on the side here, I've got x to the first. We can even put that in, x to the first, x squared, x to the third, x to the fourth. We're going to go through using the definition of the derivative. We're going to find each one of these, and then we're going to see if we can spot a pattern and write that over here for any value of n. If you've taken calculus before, you know what this is already. Luckily, though, you're all watching by yourselves, so you can't spoil it for anybody else. Okay, so we'll be referring back to this and we'll fill it in. Let me set that to the side. Let's get started with x to the first. Okay, x to the first. Using the definition of the derivative, we can set this up. F prime of x equals the limit as h approaches 0, x plus h minus x. All right, there's f of x plus h, very simple, minus the original f of x all over h. Okay. Let's see how this plays out. Well, x's cancel. H's cancel just like that. And we've got the limit as h approaches 0 of 1. And if you recall, if you're ever taking the limit of a constant, it's always simply equal to the constant. So here, for f of x equals x to the first, f prime of x equals 1. So I'm going to come back over here to my chart, and I'm just going to put a 1 right there. Okay, well, we've only done the first one. We certainly don't have enough to guess a pattern at this point. So let's keep going. Let's try f of x equals x squared. Setting up the definition of the derivative. F prime of x equals the limit as h approaches 0, x plus h squared minus x squared all over h. And okay, we need to FOIL that. All right, got our limit, x squared plus 2xh plus h squared minus x squared. So of course those x squareds cancel. And from what's left, 2xh plus h squared, we can factor out an h. Then these cancel. Finally, we can plug in the 0, and this equals just that 2x. So if f of x equals x squared, f prime of x equals 2x. All right, let's go back over here. 2x. Only 2. Let's do one more, and then I bet we can guess the pattern. Very exciting if you're new to calculus. This is what mathematicians do. You know, they plot out several, they try to get a pattern for it. Then they try to prove their pattern. That's what it's all about. Coming up with new formulas. All right, f prime of x equals the limit as h approaches 0, x plus h to the third minus x to the third over h, starting with the cube, x cubed. Here's where Pascal's triangle comes in handy. We can expand x plus h cubed. All right, we got our limit, h approaches 0, x to the third plus 3x squared h plus 3xh squared plus h to the third. And then we're still subtracting that x to the third. And it's all over h. Well, x to the thirds are gone. From what's left, we can factor out an h. Leaves us 3x squared plus 3xh plus h squared. H's cancel out. And plugging in 0 for the remaining h's, boom, boom. Those are gone, and we get 3x squared. Okay. So we'll go back over here. Now that we've done 3 of them, typically this is enough for most calculus students. Okay, so derivative of x went to 1, x squared went to 2x, x to the third went to 3x squared. And maybe like the 1 is kind of a little bit different, but these certainly, and even think of maybe 2x as 2x to the first. If you had to guess, without going through the work, if you had to guess the derivative for x to the fourth, what would you guess? And every class I've ever taught, at this point, at least a good number of people know it right away. They can see that pattern. Isn't the exponent like almost like shifting down to the front? The 3. So this would begin with 4x, and then you notice the powers are dropping by 1. So this would be 4x to the third. And that is correct. If you went through the definition of the derivative for x to the fourth, it would in fact work out in the end as 4x to the third. Even the 1, which seems like an oddball, it does still fit this pattern. X to the first, the 1 moves down in front, and then it decreases by 1. That's like, there's like an x to the 0. But if you recall, x to the 0 just equals 1. So it still works. So how would you describe that in terms of any power n? And we'd say, well, the n's going to move down, so it's n. And then the exponent drops by 1. 1 to 0, 2 to 1, 3 to 2, 4 to 3. So whatever n was, subtract 1. F prime x equals nx to the n minus 1. I'm going to write that again officially right over here. We're going to call it the power rule. And I'm going to use this notation, d over dx with the bracket x to the n, the derivative of x to the n with respect to x equals nx to the n minus 1. Huge. That's a big, big thing. Okay, we're going to stop this video here. Next video, we're going to do a bunch of examples of this and look at some more rules.